Hello, in this lecture I will talk about mathematical induction. Mathematical induction is a logical method to prove that a statement, a claim, or an equation is true for all the natural numbers. A natural number is a positive integer like 1, 2, 3, 4, 5, 6, 7, etc. We actually make two stages in order to prove that something is true for all the natural numbers by mathematical induction. In the first stage, we check whether the statement is true for n that equals to 1, and if we pass the test and it is indeed true for n that equals to 1, that's to say the statement is true for n that equals to 1, then we can proceed to the second stage. And in the second stage, we will assume that the statement is true for n, and then we will prove it for n plus 1. So actually in the second stage, we will create two equations. The first equation will be the induction hypothesis for n. Induction hypothesis for the statement that actually is the expression for n. The expression of the statement or the equation for n. And then when we rely on this assumption, that is the induction assumption or induction hypothesis, we will prove that the statement is true for n plus 1. So we have to create an expression for n plus 1. And then we will have to prove that the statement for n plus 1 is true. And we repeat again, we will rely on our assumption that the statement is true for n to prove that the statement is also true for n plus 1. Okay, now I will explain the logic behind the mathematical induction proof. Actually, in the first step, we verified that the statement is true for n that equals to 1. And while in the second stage, we actually proved that if the statement is true for n, then it must be true also for n plus 1. So in this way, we actually proved that the statement is true for all the natural numbers, and I will explain why. Because in the first step we proved that the statement is true for n that equals to 1. So we know for sure that the statement is true for n that equals to 1. And then for the second stage, we can actually prove, we can deduce that the statement is also true for 1 plus 1, because we proved in general that if it is true for n, it also must be true for n plus 1. And now n is equals to 1. So if it is true for n that equals to 1, it also must be true for 1 plus 1, or for n that equals to 2. Okay, so in this way we actually proved that the statement is also true for n that equals to 2. And then we actually repeat on the same step, on the same process, in order to prove that the statement is also true for n that equals to 3. Because we can say that now we know that the statement is true for n that equals to 2, and for our general proof that if it is true for n, it also must be true for n plus 1, we can deduce that because of the fact that the statement is true for n that equals to 2, it also must be true for 2 plus 1, because of our general proof that if it is true for n, it also must be true for n plus 1. So n equals to 2. We know that it is true for n that equals to 2, so it also must be true for n that equals to 2 plus 1, that is to say for n that equals to 3. And then we actually repeat on the same process in order to prove that it is also true, that the statement also true for n that equals to 4, because we can say now that we know that the statement is true for n that equals to 3, it also must be true for n that equals to 3 plus 1, because of our general proof that if it is true for n, it also must be true for n plus 1. And now n is equals to 3. So it also, if it is true for n that equals to 3, it also must be true for n that equals to 3 plus 1. That is to say, it is also true for n that equals to 4. Okay? So in this way we actually proved, and in this way we will prove that it also true for n that equals to 5, to 6, to 7, and so on. So in this way we actually proved that the statement is true for all the natural numbers. So by actually passing the 2 stages, by doing the 2 stages in success, if we verify that the statement is true for n that equals to 1 in the first stage, and in the second stage, if we succeed to prove that if the statement is true for n, it also must be true for n plus 1, we actually proved that the statement is true for all the natural numbers. Okay, so that is the logic between mathematical inductions proof. Okay, so now in order to clarify the topic, I will give you 2 examples. We will start with the first example. It will be 1 plus 2 plus 3 plus n equals to n times n plus 1, all divided by 2. So we actually want to prove that this statement is true for all the natural numbers. Okay, so we'll start with the first stage. In the first stage, we will check if the statement is true for n that equals to 1. So we will verify that the statement is true for n that equals to 1. As I've already told you, we can proceed to the second stage only if we succeeded to pass the first stage. So we have to prove that the statement is true for n that equals to 1 in order to proceed to the second stage. So we will check now the statement which is true for n that equals to 1. So in this side of the equation we have only 1 that equals to n times n plus 1 divided by 2. N equals to 1, so it is 1 times 1 plus 1 divided by 2 equals to 1 times 1 plus 1 is 1 times 2 divided by 2. 1 times 2 is 2 divided by 2, and 2 divided by 2 is 1. So we actually have here an identity, 1 equals to 1. So we succeeded to prove that the statement is true for n that equals to 1. Okay, as you can see here, we checked if the statement is true for n that equals to 1. So because n equals to 1, we have in this side of the equation 1, and in the other side of the equation we have n times n plus 1 divided by 2, and n equals to 1. So n is 1. We can put here instead of n 1. 1 times n plus 1 is 1 plus 1, all divided by 2. So n times 1 plus 1 is 1. 1 times 1 plus 1 is 1 times 2 divided by 2, and 2 divided by 2 is 1. So 1 equals to 1. So we verified that the statement is true for n that equals to 1. So we passed the test, and now we can proceed to the second stage. In the second stage, as I already told you, we will assume that this statement is true for n, and when we rely on this assumption that this statement is true for n, we will prove that it's also true for n plus 1. So we will create here two equations. The first equation will be the inductions hypothesis. Okay, inductions hypothesis. We assume that the statement is true for 1, so this is the inductions hypothesis. So we will create the statement, the expression for the statement for n. So actually it will be the same expression of the original statement itself. Okay, so we will copy it here. It will be 1 plus 2 plus 3 plus n equals to n times n plus 1 divided by 2. Okay, so it is all exactly the same expression as the original statement. So this is the expression for n, and we assume that this equation is true. And when we rely on this assumption, this is the induction hypothesis, and when we rely on this assumption, we will prove that the statement, the original statement, this original statement is also true for n plus 1. So we'll create the expression of the statement for n plus 1. It will be, instead of n, now the expression is for n plus 1. So it will be 1 plus 2 plus 3 plus n plus n plus 1, because of the fact that the second equation is the expression for n plus 1. So we will add numbers here until we arrive to n plus 1, and it also includes n plus 1, and all equals. So in the original equation we have n times n plus 1 divided by 2, and now we want to create the expression for n plus 1. So instead of n, we will write n plus 1, or we will substitute n by n plus 1. So the expression will be, instead n, we will write n plus 1, and in the brackets we have also n plus 1, and we have plus 1, so it will be n plus 1 plus 1, all divided by 2. Okay, so actually the second equation is the expression of the statement for n plus 1, and we will prove that this statement is also true. We must prove that this second statement is true when we rely on the assumption that the second equation is true. Okay, but here we have n plus 1 plus 1, so it is n plus 2, so we will write it down. So the second expression that we have to prove is for the statement for the case of n plus 1, so it will be 1 plus 2 plus 3 plus n plus 1, because this expression is for n plus 1, so n plus 1 must be included in the expression. And as I've already told you, we have here n plus 1 times n plus 1 plus 1, so it will be n plus 2, and all divided by 2. So we will write here n plus 1 times n plus 2, all divided by 2. So we must prove that this equation is true, and actually, as I've already told you, this equation is the expression of the statement for n plus 1. Okay, and as I've already told you, we will rely on our inductions hypothesis on equation 1 that the statement is true for n, and as we rely on this assumption that expression 1 is true, we will prove that the expression 2 for n plus 1 is also true. Okay, so in order to prove that expression 2 is true, we actually should look in this expression. It is 1 plus 2 plus 3 plus n. Okay, and actually it is exactly the same expression as we have in the induction hypothesis, 1 plus 2 plus 3 plus n. And as you can see, this expression in the green color equals to n times n plus 1 divided by 2. And actually this expression equals to this expression. They are identical. So, and this expression equals to this expression, so we can substitute 1 plus 2 plus 3 plus n by n times n plus 1 divided by 2, because they are equal to each other. So we will do it now. So instead of 1 plus 2 plus 3 plus n, we will write in the second expression n times n plus 1 divided by 2. We can substitute between them because they are equal to each other. Okay? And then we will copy the rest of the equation as it is. Okay? Plus n plus 1 equals to n plus 1 times n plus 2 divided by 2. Okay, so this second equation we have to prove that it is true, and this expression is actually the expression for n plus 1 of the statement. Okay, so in order to prove that equation 1 is true, we will divide both sides of the equation by n plus 1, because we have n plus 1 in both sides of the equation. Okay. N times n plus 1 divided by n plus 1 is n divided by 2, plus n plus 1 divided by n plus 1 is 1, equals to n plus 1 times n plus 2 divided by n plus 1 is n plus 2, all divided by 2. So I'll show it again. N times n plus 1 divided by n plus 1 is n, divided by 2, and n plus 1 divided by n plus 1 is 1, and n plus 1 times n plus 2 divided by n plus 1 is n plus 2, and we divided by 2. So we can actually separate this expression to two parts. It will be actually n divided by 2 plus 2 divided by 2. Okay. Okay, so we separated this expression to two parts, and we got that n plus 2 divided by 2 equals to n divided by 2 plus 2 divided by 2, okay? According to the mathematical rules. Okay, and 2 divided by 2 here is 1. Okay, so we will write it down. So we have here an identity. So n divided by 2 plus 1 equals to n divided by 2 plus 1. So we actually proved that the second equation for n plus 1 is true, or in other words, what we have proved is that if the statement is true for n, if the original statement if this statement is true for n, then it also must be true for n plus 1. Okay, so we can summarize that in the first stage we proved that this statement is true for n that equals to 1, and in the second stage we proved that if the statement is true for n, it also must be true for n plus 1. And in this way we actually proved that the statement is true for all the natural numbers, as I have already explained to you previously. Okay, so we finished for the second example, and now I will give you the second example. In the second example, it is actually 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 equals to n squared times n plus 1 square, all divided by 4. So we actually have to prove, I forgot, so I will correct it. The statement is 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 square divided by 4. So we actually want to prove that this statement 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 squared divided by 4. So we will start with the first stage. That is to say, we will check if this statement is true for n that equals to 1. Okay? Check for n that equals to 1. Okay, so in this side of the equation we have 1 to the power of 3 because n equals to 1. And in the other side of the equation we have n squared times n plus 1 squared all divided by 4, and n equals to 1, so it will be 1 squared times 1 plus 1 squared divided by 4 equals to n squared. 1 squared is 1, 1 plus 1 is 2, so it is 2 squared all divided by 4. 2 squared is 4, so it is 1 times 4 divided by 4. 1 times 4 is 4, and 4 divided by 4 equals to 1. So 1 to the power of 3 is 1 equals to 1. So we actually passed the first stage. We verified that the statement is true for n that equals to 1, because we have here identity. Okay, so now we can proceed to the second stage. That is to say, we will assume that the expression this expression is true for n, and we will prove it for n plus 1. And the proof for n plus 1 will be by relying on our assumption that this statement is true for n. Okay, or actually we will rely on the induction's hypothesis that the statement is true for n. So actually we will create two equations. The first equation will be the induction's hypothesis. It will be 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3. So this is the induction's hypothesis equals to n squared times n plus 1 square all divided by 4. So I will write it here. It is the induction's hypothesis. So we actually assume that the statement for n is true. Okay, so this is actually the first equation is the induction's hypothesis. We assume that the statement is true for n. and the statement is for n is exactly as the original statement. Okay, it is actually no, 1 minute please, we'll put it here. Okay, the statement for n is exactly as the original statement. That is to say, it is 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 squared, all divided by 4. Okay, so this first equation is the induction hypothesis. We assume that this equation is true. Okay, now we will create the second, it is induction hypothesis or induction assumption that the statement is true for n. Okay, now we will create the second expression of the statement for n plus 1, and after we will create the statement for n plus 1, we will have to prove that the statement for n plus 1 is true, and we will rely on our assumption or our induction assumption that is the statement is true for n in order to prove that the statement is also true for n plus 1. So first of all, we will create the statement for n plus 1. It will be 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3. You should remember that it's the statement for n plus 1, so we must add also plus n plus 1 to the power of 3. Okay, because in the statement for n plus 1, we also must include n plus 1 to the power of 3, because it is the statement for n plus 1 equals. So in the original statement we have n squared times n plus 1 squared divided by 4, and in the original statement actually it is the statement for n, and we want to create the statement for n plus 1. So wherever is written n in the original statement, we will write n plus 1, because the second equation is the statement for n plus 1. So we must substitute n in the original statement by n plus 1. Okay, so here it is n squared, so we will write n plus 1 squared here, and we have here n plus 1 squared, so it will be n plus 1 plus 1, because we substituted n by n plus 1, and we have to add also 1, so it will be n plus 1 plus 1 all squared divided by 4. So the statement that we have to prove for n plus 1 will be 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 plus n plus 1 to the power of 3 equals to n plus 1 square times n plus 1 plus 1 square, all divided by 4. But n plus 1 plus 1 is n plus 2, so we will write it down. Okay, as you can see here, the only change from this row to this row is instead of n plus 1 plus 1 we wrote n plus 2. All the other things is exactly the same as this row. Okay, so in order to prove that the second statement is true, we should look on this expression. That is in the green color. Actually, this expression is identical to this expression, but this expression equals to n squared times n plus 1 squared divided by 4. And because of the fact that this expression equals to this expression, so this expression equals also to this expression. So we can substitute the two expressions between them. Okay, so instead of 1 plus 2, 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3, we will write n squared times n plus 1 squared, all divided by 4. Why? Because they actually equal to each other, so we can substitute between them. Can substitute. Okay. Equals. So we will copy the other parts of the equation as it is, plus n plus 1 to the power of 3 equals to n plus 1 squared times n plus 2 squared, all divided by 4. Okay, so we substituted this expression by n squared times n plus 1 squared divided by 4 because they are equal to each other, and the other parts of this equation we copied it as it. We didn't change them. We copied them here, and we have to prove that the second equation is true. So in order to prove that this expression is true, we will divide both sides of the equation by n plus 1 square, because we have n plus 1 square in both sides of the equation. So n squared times n plus 1 squared divided by n plus 1 squared will be n squared, and we divide it by 4, plus n plus 1 to the power of 3 divided by n plus 1 squared will be n plus 1. It equals to n plus 1 square times n plus 2 square divided by n plus 1 square will be n plus 2 square, and we divide it by 4. Okay. So here as I've already explained to you, n plus 1 square times n plus 2 square divided by n plus 1 square will be here n square times n plus 1 square divided by n plus 1 square will be n square and divided by 4. N plus 1 to the power of 3 divided by n plus 1 square will be n plus 1, and it is equals to n plus 1 square times n plus 2 square divided by 4, and when we divide it by n plus 1 square, the outcome will be n plus 2 square divided by 4. So that is what is written here. Okay, so we have to prove that this statement is true, and in order to prove it, we will multiply both sides of the equation by 4. Okay, and then we will get that n squared divided by 4 times 4 will be n squared plus n plus 1 times 4 will be 4n plus 1 equals to n plus 2 squared divided by 4 times 4 will be n plus 2 squared. So we'll multiply both sides of the equation by 4. So n squared divided by 4 times 4 is n squared, and n plus 1 times 4 is 4n plus 1, and n plus 1 squared divided by 4 times 4 will be n plus 2 squared. So now we will open the brackets in both sides of the equation. We will get that n squared plus 4n plus 4 equals to n squared plus 4n plus 4. So we got an identity because here it is n squared and 4 times n is 4n, 4 times 1 is 4 equals to n plus 2 squared. It is like a plus b squared, that is a squared plus 2ab plus b squared. So here it will be n squared plus 2 times 2n is 4n plus b squared, it is 2 squared, it is 4. So we got an identity. That is to say, we proved that the second statement for n plus 1 is true. We actually proved that if the original statement is true for n, if this statement is true for n, then it also must be true for n plus 1. And we can summarize that example, the second example, and we can say that in the first stage we proved that this statement is true for n that equals to 1, and then we actually proved that if this statement is true for n, then it also must be true for n plus 1. And actually in this way we proved that this statement is true for all the natural numbers, as I have already explained to you in the beginning of the lecture. So we can summarize the lecture, and we can say that mathematical induction is a logical method to prove that a statement, a claim, or an equation is true for all the natural numbers. And the natural number is a positive integer, like 1, 2, 3, 4, 5, 6, 7, etc. And we actually do 2 stages in order to prove that something is true for all the natural numbers by mathematical inductions. In the first stage, we will prove that the statement, or will verify that the statement is true for n that equals to 1, and only after we passed this test we can proceed to the second stage. And in the second stage we will assume that the statement is true for n, and we will prove it for n plus 1. Actually, we will create 2 equations. The first equation will be our assumption or induction's hypothesis, or induction's assumption that the statement is true for n. And when we rely on this assumption, we will prove that the statement is also true for n plus 1. So we will also create the second equation for n plus 1, and we will prove that it is true when we rely on our assumption that the statement for n is true. Okay, so in this way we actually proved that the statement is true for all the natural numbers, because in the first stage we verified that the statement is true for n that equals to 1. And then in the second stage we assumed that we actually proved that if the statement is true for n, it also must be true for n plus 1. So now that we know for sure that the statement is true for n, it also must be true for n plus 1 according to our general proof in the second stage. Okay, we proved in the second stage if the statement is true for n, it must be true also for n plus 1. So now that we know that the statement is true for n that equals to 1, it also must be true for n that equals to 1 plus 1. That is to say, it is also must be true for n that equals to 2. And after we already know that the statement is true for n that equals to 2, we will do the same process in order to prove that the statement is also true for n that equals to 3. And we can say that we already know that the statement is true for n that equals to 2, and according to our general proof that if it is true for n, it also must be true for n plus 1, and now n equals to 2, then we know that it is true for n that equals to 2. It also must be true for n that equals to 2 plus 1. That is the n plus 1. And 2 plus 1 is 3. 2 plus 1 is 3. So we know now that the statement is also true for n that equals to 3. And we will repeat on the same process again in order to prove that the statement is also true for n that equals to 4. Because we know already that the statement is true for n that equals to 3. And we will rely on our general proof that if it is true for n, it also must be true for n plus 1. And now that n equals to 3, it also must be true for n that equals to 3 plus 1, that is 4. So in this way, we actually proved that the statement is also true for n that equals to 4, and we will continue in this way in order to prove that the statement is true for 5, 6, 7, etc. And that is the reason that in this way we actually proved that the statement is true for all the natural numbers. Okay? Thank you very much.